is going to be about building a database with Python. We're going to start with talking about what HDB is, so that you guys understand the context of the talk and the extent of the problems that we had to deal with, and the extent of the code base, actually. The goal of this talk is that we can just go home with the knowledge about HDB and its internals and just re-implement HDB from scratch in about 5 years. So what is HDB? HDB is a new relational database built on top of PostgreSQL. And the concept of building a database on top of another database isn't exactly new. There are a bunch of NoSQL databases, for example, that build on top of RocksDB or LevelDB. It's normal. We are just elevating this concept further, and instead of building on some super low-level database, we're building on a high-level database, on top of a high-level database, which is PostgreSQL. PostgreSQL is reliable, it's robust, it's universally trusted, it's open source, it meets all the right qualities. Sure. Can you hear me now? So instead of focusing on the low-level specifics of database operation, we are focusing more on the developer experience and some other high-level features of relational database. So ultimately, the goal that we have in mind is to make people fall in love with relational databases again. It's rare that developers actually like relational databases, or if they like SQL, or if they even understand it. Even though the technology itself, relational databases, they are amazing, they're great, they're a great piece of tech. So what does HDB brings to the table? It brings a new query language. It brings its own fresh take on the relational data model. Some promising features like migrations, for example, are solved right in the core of the database. It has well-designed CLI, it supports GraphQL, and thanks to, again, being built on top of PostgreSQL, it's reliable and fast. Most importantly for this conference is that it's built with Python, mostly. So this is kind of a glimpse of what a schema in HDB looks like. It's probably a little bit too small for you guys to read on the screen. But the idea is that schemas in HDB can be defined in two ways. You can either use low-level DDL commands, like create type, create link, create property, or something like that. Or you can just describe your schema in a file using a special language, which we call schema declaration language. And if you look closer at the syntax that we have here, there, you will recognize that you don't actually need to know this syntax to understand what is it about. You can easily declare types, abstract types, relationships between those types, properties, and links between the types. It kind of looks like, I don't know, TypeScript interfaces or Python data classes to you, except that it's language agnostic. So you can use HDB with pretty much any language. The schema is still going to be the same, and the mechanism of the schema are not going to be different based on what language you're interacting with it. HDB has advanced and strict type system, and in fact, it's in some corner cases it's even more strict than PostgreSQL itself. The type system supports multiple interesting features. One of them is multiple inheritance. This is how we implement polymorphism. Basically, it's similar to Python or mixins in some other languages. The advantage of this model over what a relational database typically offers is that HDB type system is high level already. You don't have to use ORMs or some libraries or build like any sort of like boilerplate code to just work with the type system and build on top of it or integrate it in your language. It's already pretty much there. Programmers, we don't think in tables. We actually think in types or in structs or in classes. And this is what HDB basically exposes natively. And of course, HDB comes with all the regular features that any relational database must have. It supports indexes, constraints, abstract types, user-defined functions, introspection, and everything else. And this is a sneak peek at our query language. And if there is like one thing that can quickly kind of give you an idea of what HQL looks like, it's as if GraphQL and SQL had a child. That would be HQL. It kind of looks like GraphQL because it allows you to easily fetch nested hierarchies of types and objects. And it's kind of like SQL because it's fairly advanced. It's composable. You can have complicated expressions everywhere you want. You can do analytical queries with HQL. That said, it's strict. It's the TypeScript strict type language. It's a declarative one, and one of the design goals of HQL was to basically make it surpass SQL in power. Already, you can do some things in HQL that would be pretty hard to actually do in SQL. And of course, it supports all the, again, advanced features that you need, like subqueries or nested mutations or combining multiple different inserts and deletes and updates in one query. We can do some pretty amazing stuff with HQL. So ultimately, HDB is packed with different features. As I said, it supports GraphQL. We have, I think, best-in-class JSON support. You can do pretty interesting things with JSON and NDB. In HDB, you can cast complex types and complex shapes to JSON, and you can construct things fairly quick. Whereas in PostgreSQL, you would be calling bunch of different functions. In HDB, we have high-level syntax constructs that just allow you to build JSON super quickly. We have some interesting workflow innovations, I would call them. We have, for example, a thing that we call HDB projects, and it's kind of similar to Python virtual environments. Basically, you can have multiple different projects on your disk, and each of those projects can have a separate database, a separate version of the database. But when you are inside that project, you can just connect without any arguments. You can just use your CLI, and HDB automatically understands which instance of the database you're talking to. This is actually incredibly convenient. We will soon, probably after 1.0 release, which will happen in about 3 to 4 weeks, we will introduce access control policies, something that has been a long-awaited feature, which would basically allow you to specify access control policies right in your schema, and then the same query would just behave differently based on, for example, what kind of user privileges you have or anything else, really. The system is incredibly flexible. We've been kind of quiet about HDB operating in the stealth mode on purpose, simply because it's a relational database. Once we commit to the APIs, to the language syntax, to our schema, we cannot actually release a new version of HDB and just roll some of those decisions back. We have to support them for years to come. So we spent years actually working on HDB and making sure that all the APIs and data models and query languages that we have are sound and that we can live with them for a long time. We will soon release 1.0, as I said, in about 3 weeks, maybe months. And after that, we will become definitely more vocal about HDB, saying that people should try it. Anyways, enough about HDB itself. Let's talk about the architecture of HDB, and let's talk about the role of Python in that architecture. So HDB loves Python. HDB is coded primarily in Python, at least its core parts. And the question is, why? Traditionally, people use different languages to create things like databases. Usually it's C or C++, maybe Java or Golang or recently Rust. So when when we started with HDB, we didn't actually have a clear understanding that, hey, this is going to be a database. We started many years ago, and even originally, HDB was sort of an ORM for Python. So the first reason, I guess, is historical. We knew Python well. We started with Python, and we continued to use Python. But then we also understood a few things. Python allows for incredibly fast iteration, especially now with MyPi. Just refactoring your entire application can be done reasonably quickly with Python, as opposed in some more rigid languages like Rust or C++. Sometimes you would need to do a fairly complicated rewrite of your program. So if you really don't have a 100% clear picture of what you're building, starting with Python actually makes a lot of sense. Python is also open to contributions. And over the years, we contributed a lot of things to Python. It's not obviously super easy, but it's definitely possible to become a Python core developer. And if you have a complicated feature or an interesting feature to contribute to the language, you can convince other core developers to do that, and then you have it in your language. I'm not sure of any other language that has this streamlined process that is pretty much open to everyone to contribute successfully something to the language, and especially things like changing syntax or something like that. Usually it's kind of reserved for the insiders. Python is incredibly open in that regard. And Python actually rapidly evolves to this day, which is quite surprising for a language of its age. Just recently we got support for pattern matching. In the next version of Python, we will likely have exception groups, which will simplify some aspects of async await programming. Mark Shannon and his team are working on speeding up Python, so hopefully we'll see Python becoming faster and faster and faster from now on with each new release. So Python is great. It's open, it's quick to iterate with, and it's still evolving, which is cool. So there are multiple different moving parts in HDB. HDB is a huge product. The two things that we're going to talk about today is the core parts of HDB, which is the I/O server and the compiler stack, both of which are written in Python. There are multiple other things like client libraries and the command line interface, which is actually a pretty big project on its own. There is also upcoming HDB Cloud, which is a huge project, and some of those things are using Python exclusively, some of them just using it in some way, but I/O server and compiler are pretty much exclusively Python. So we're going to talk about those two components. So the I/O server part of HDB has just a few things that it has to cover, which is managing client connections to HDB. Then it's about orchestrating PostgreSQL instances. Remember, HDB is built on top of Postgres, so it fully controls and kind of envelopes PostgreSQL. And then to also orchestrate compilers, which we're going to talk a little bit later. So when we started to work on the I/O server, we had some basic requirements pretty much that, first of all, we wanted to be able to handle a lot of connections concurrently. And second, opening a connection must be cheap to HDB. If you know anything about PostgreSQL architecture, for example, when you connect to PostgreSQL, it usually spawns a process. So connections to Postgres are pretty expensive, and this is why people put things like PG Bouncer or PG Proxy in front of Postgres to kind of create this pool of connections for you. So we thought hard about this at HDB and decided, hey, we don't actually want people to deal with these things. How about HDB just does it out of the box for you? You shouldn't be bothered with setting up all of this advanced architecture and advanced stack on top of your database. The database should be just able to handle it for you. Then again, by nature, we have things that just execute asynchronously, Postgres servers and the pool of HDB compiler processes, and they're all kind of asynchronous. So handling asynchronous notifications also was kind of requirement. So asyncio was a clear choice for HDB. So IO server in HDB is an asyncio application, and then from the get-go, we knew that we need to make IO server basically as fast as possible, and because asyncio is written in Python, in pure vanilla Python, it naturally has some runtime overhead. So this is how uvloop was born. This is a little known fact about uvloop, but basically it was created for HDB to make sure that I/O in HDB is as fast as possible. Generally, uvloop can provide up to 4x speed up of your application. You just drop a line, import uvloop, then uvloop.install, and that's all you want to do. Your program will just become faster. In HDB case, it makes HDB about 3 times faster than it would be with vanilla asyncio. But there are some other good reasons to actually use uvloop. The first one is that it's not actually tied to CPython release cycle. So if we need to add a feature or some sort of debug API, or we need to fix a vulnerability or some bug or annoyance in uvloop, we can just do it. We don't really care about releases. We can release multiple times a day if we absolutely have to. So this is another reason why actually running uvloop in your environment might be beneficial. And for us, it also makes sense because we created it, so we fully control it. If we miss some feature, we can just go and add it. It's our project, so we use uvloop. And then the IO server part specifically heavily uses Cython. Pretty much 90% of the code base is in Cython, and it provides significant speed up. So the thing with Cython is that if you just compile your Python code with Cython, it might make it 30% faster, maybe 20% faster, basically by just eliminating the overhead of the C-eval loop. But it's still going to be using the Python object model and the entire Python C API behind the scenes. The only way for you to actually achieve a significant speed up is to kind of go all in and just use all of the syntax extensions that Cython provides. So you end up with a bunch of pyx files, which is Cython native files with some weird Cython syntax. But then it can eliminate a lot of things like attribute lookup, for example, because it will just compile your code to use C structs. It will make your function calls faster because instead of using Python calling convention, it would use C calling convention. You can basically drop down and do some memory operations if you want, just as you would be doing in C. You can manually mutate buffers and do some unsafe pointer arithmetic if you want, and we do that a bunch actually in HDB core. But then, as opposed to C, we also have asyncio in Cython. So your code can be reasonably high level and have like this high level structure and organization. And then when you need to do some direct memory manipulation, you can do that as well. There are some downsides to in using Cython. As I said, the language itself, it's not as elegant as Python. Sometimes it feels a little bit hacky. There is not a lot of integration for Cython, like IDE support is kind of not so good. But then again, if you need absolute performance from a Python-like code, then Cython is the way to go, at least for now. So those were kind of just the infrastructure bits, I guess, or like what you can do with extra tools and extra runtimes to make your code faster. But also a lot of the performance can be squeezed by just properly designing your service. And we paid a lot of attention in HDB to just make sure that HDB will work as fast as possible. So first, and it's true for any application or any service, you just need to make sure that your fast path is actually as fast as possible. And that that involves many different things, like, for example, to make sure that your communication channel between the server and the client doesn't have unnecessary round trips, for example. Ideally, you should just send one request and get one response. And this is what we do in HDB. It's not true for all other databases. In PostgreSQL, you might end up exchanging several request responses before you get results for your query. And this is where it might become slower than necessary, especially if there is some network latency involved. So in HDB, we carefully designed our binary protocol to just eliminate like all the extra round trip. Then compilation of queries is actually expensive because you have to parse an HQL query or a GraphQL query, you have to validate it, you have to compile it, and it's a lengthy process. So ideally, you shouldn't do that often. And there is one observation about any application is that applications don't usually have an infinite number of queries. The number of queries is actually usually pretty limited. So if you can cache them, that's great. So this is what we do. But then what happens if you, for example, just inline some constants in your queries? So one of your query can be select 42, and the other query can be select 1. They are essentially the same queries. They're just like different by one constant. So in order for us to speed up executions of these queries, we do this trick. We lex those queries. We extract constants, replace them with parameters, and then we can cache them. This particular path we just implemented with Rust. So we have a Rust tokenizer of HQL and GraphQL. It's extremely fast. So we tokenize the query, we extract constants, and all of that is done in Rust. It's a relatively small code base. And that's basically it. We don't have anything else beyond asyncio, uvloop, Python, and a tiny little bit of Rust in our server I/O code base. So is server I/O in HDB fast enough? Well, apparently it is. We probably cannot see the benchmark numbers on the small screen. You can go to hdb.com, open our blog, and open the Alpha 1 and Alpha 2 announcements, which actually describe the benchmarks that we have in great detail and the methodology. But basically, in our benchmarks, they're kind of comprehensive benchmarks. So they test different scenarios of how you can interact with your database, different libraries and different languages. So for Python libraries and ORMs, HDB can be anywhere from 2 to 4 to 5 times faster. For some JavaScript popular ORMs, we are faster than them by a factor of 1,000, which is just mind-boggling. So clearly, HDB I/O is kind of good enough, and Python allowed us to get there. So does Python actually work for us for the server I/O component of the system? Well, yes, it does. But there are some caveats. One of them is that currently we have a known limitation that if you have a very massive PostgreSQL backend behind HDB, we're not utilizing it fully. We need to implement what's called end-to-end scheduling with HDB, and we'll have to do some interesting inter-process communication to do it properly because of GIL. We cannot just have several event loops in one process. It's doable, and this is something that we will do relatively soon, and it will bring some nice speed-ups. In somewhat distant future, though, we might actually considering rewriting the server part of HDB in a language like C++ or Rust, simply because we want to support things like HTTP2 and HTTP3 and live streaming and get rid of GC pauses in the I/O process. We might actually go that route. It's possible. It's still going to be a pretty involved project. So in the foreseeable future, it's unlikely that we'll be doing that. Python is definitely good enough. Maybe in the future we'll do that. Let's quickly talk about the compilers in HDB. They're also written in Python, and this is basically, I think, 80% of HDB code base is just different compilers. We have a bunch of them. So our query language, which is called HQL, we compile it internally to intermediate representation. And before that, we have to parse it, we have to validate it, and then we compile it to IR. Then we can compile IR to SQL. We also have a compiler for GraphQL to HQL, and this is how we execute GraphQL. And there is also a huge machinery for just validating your database schema, drive the migrations engine, and things like that. A couple of observations about our compiler infrastructure. First one is kind of funny one. We use a lot of single dispatch in our compiler. It's surprisingly useful to write code like that because you can eliminate nesting. It's faster than the popular visitor pattern that I think almost everybody is using. It makes code just easier to follow and easier to read and better organized. So this is just like a nice, interesting detail about our code base. So if you're working on something like a compiler, just give single dispatch a try. It's a nice little helper API. The bigger thing about compiler, and I think this is what makes HDB code base sort of unique, is that we use a lot of immutable data structures. It's actually quite interesting because this idea of using immutable data structures in HDB, I think it was motivated by my work on adding context variables to Python. Because back then I just did a research. How do functional languages like Clojure, for example, how do they actually manage immutable data? So I discovered this interesting data structure called hashed array map tries. I implemented that for CPython, and then we started to reuse this code, and we ship it now in the immutables package. You can install it from the PyBay. But in HDB, it's pretty much fundamental now that we use immutables, because immutable state allows you to do interesting things to it. For example, you can support transactions. This way, you can make your state transactional because you never actually mutate anything. It also allows you to do better caching in your system, because if you have a huge immutable data structure, you don't have to just recursively compare it to different to structures. You just compare basically, are they the same object or not? And if they are, well, it's the same data. So we take advantage of that in our RPC protocols and pretty much everywhere else. So immutability is a pretty cool thing for us. We also just fully embraced MyPi. We spent about 3 months on strictly type annotating our code base. It was sort of painful, but it brought massive quality of life improvement. It's so much easier to refactor right now. It's so much easier to just rely on our CI now to catch some weird things and unsafe refactorings. So I can definitely and wholeheartedly just recommend to use MyPi. An interesting thing about MyPi is that it has a plugin API. So in HDB codebase, we have a few interesting data structures that are a little bit too magical for MyPi to just understand. So we created MyPi plugins to make MyPi understand those things. So again, if you have something unusual in your Python code and code base, and you don't know how to make MyPi work with it, explore the MyPi plugin API. What's next is probably for us to try MyPi-C. The performance of our compiler infrastructure is it needs improvement, and we hope that MyPi-C can help us with that. I definitely believe in that MyPi-C will have a bright future, simply because I have a lot of experience dealing with Python, and I know how fragile that thing is. And I just wish that I could just write strictly typed Python code and just compile it to something low level and fast. And this, MyPi-C basically can fulfill that promise. And Yeah, it's probably going to be one of the next big things that we're going to be trying for MyPi for HDB is trying to use MyPi heavily. Thankfully, Michael Sullivan is with us, and he's one of MyPi core developers. So hopefully, we'll be able to contribute like any improvements that we need to do in MyPi or MyPi to make it actually happen. I'm looking forward to it. Okay. Some other tidbits. So we have lots of tests in HDB. We have over 4,400 of tests, and those are not unit tests. Those are every test is basically an integration test. Every test might have a bunch of different queries, and those queries actually touch a lot of different aspects of the system. So those tests are pretty heavy to run. We use standard unit tests for them, but we do have a custom test launcher that we created specifically for HDB because our test flow is actually quite complicated. And thanks God we did it. So if we just run tests sequentially, it takes about an hour. But if you have one of those fancy Threadripper machines, running tests with J32 brings it down to 3.5 minutes. Which is amazing. So this is another recommendation I can give. If your project has lots of unit tests and you cannot otherwise speed them up, try to make them run concurrently. And speaking of concurrently running tests, so we had this limitation on GitHub Actions. So the virtual machines that run your GitHub Actions, they are limited. You can use J2, and that would be it. So running our test suite a few months ago on GitHub was about 40 minutes or 50 minutes per run, which really made it hard for us to just merge PRs relatively quickly. So we employed an interesting solution to that. So we basically analyze our test suite. This is done automatically after it's run. And we just automatically segregate tests in different buckets. And then we automatically parallelize these buckets into like separate GitHub Action jobs. So if you look at any HDB PR, you will see that there are like 18 CI actions that are just running in parallel. And that brings down the current CI time to just 8 minutes from 1.5 hours, which is also amazing. And I haven't seen projects do it this way. So does Python actually work for HDB compilers? Well, yes. But we do need to improve the performance. Hopefully, MyPi will help us with that. Rewriting our compiler infrastructure in any other language is probably off the table for the foreseeable future, and I'm not sure that we will ever do this. We'll just try to keep pushing Python forward past its limits, I guess, to make the performance more and more acceptable. But to kind of sum it up, Python is a wonderful language, and a lot of people don't understand that it's rarely a bottleneck in your application. You can push Python pretty far, and you can get amazing performance out of it if you just invest heavily in the ecosystem and use the right tools.